as promised, today we're going to look at the second half of example 14.4. It's still a conservation of energy type of problem, but we've got some different information, so it's like we almost have to work backwards from what we did before. So let's look at this problem. Let's see how it's set up. A negative 0.21 millicoulomb particle, mass 3.1 kilograms, and so that's this particle right here, is given an initial velocity of 15 meters per second away from a 0.45 millicoulomb stationary charge. So here's our stationary charge, and it says that it's given an initial velocity away from it. Now, before we go any further and just reading the problem, let's look at these two charges. What do we expect that, given to their own devices, what is this particle going to naturally do? Well, it's going to naturally, what? It's going to naturally be attracted because these are opposite charges. So naturally, this is going to want to move towards this. But it says that the initial velocity that it is given, so basically we've given it a shove and it's going this direction. It's going away from it. So what's ultimately going to happen? Well, it's going to go away to a certain point, and then this force is going to overcome its velocity, and it's going to turn around and it's going to go back the other direction again because it's going to be attracted to this charge. So at some point it's moving away this direction, but at some point it's going to slow down, slow down, slow down. It's going to stop, and then it's going to reverse direction, and it's going to go the other direction. And so the rest of the question says then, the particle's initial position is 33 centimeters or 0.33 meters from the initial charge or from the stationary charge. How far away will it be able to travel before it gets pulled back? So what I'm being asked is, what is that distance right there? How much further is it going to be able to go before it starts traveling back the other direction again? Okay. Excuse me. So, I'm kind of catching a cold here. So hopefully you're not having too much trouble understanding me, as the more I talk, I get froggier and froggier. Okay, so we know that this kinetic energy is going to be transformed strictly into potential energy once it gets out here, because the kinetic energy is going to go away. When it gets out here, I'm not going to have any kinetic energy left because it has to stop in order to turn around and go the other direction. So I can start out by calculating the amount of kinetic energy that my particle has. So kinetic energy is 1/2 mv squared. So I have 1/2 times 3.1 kilograms times 15 meters per second, that quantity squared. And so the kinetic energy that I have here is a total of 350 joules, okay? So I know that I'm going to lose that much kinetic energy because it's going to come to a stop. And so when you lose kinetic energy, that corresponds to a gain in potential energy. So if I have a gain in potential energy, I know what that looks like. It's going to look like this. So my gain in potential energy, this is how much kinetic energy it has. It's going to lose it because it's going to stop. So this is going to be a gain in kinetic energy. So that's going to be 350 joules. Now notice this is a little different from what we did before. Before I had a negative number that I had to change to a positive number. So you've got to really think about the physics of the situation to understand what's going on to make sure that you don't goof up your signs. Okay, so the charge that I'm talking about is this movable charge right here. So the charge is negative, a negative 0.21 times 10 to the minus 3 coulombs times delta V. And so when I solve that, my delta V comes out to be a negative 1.7 times 10 to the 6th volts. All right, so that's the delta V. Well, what do I do with that now? Well, I have Remember, we have an electric field here, and I have two positions. I have this position here where it starts out, and I'm going to have this position over here. And at each position, I can calculate what the electric potential would be. Well, I don't know this distance here yet. That's what I'm trying to figure out. But I can calculate the electric potential here. And so since I can calculate it here, that's a capital V initial, which is KQ over R. And so I've got K, 9.0 times 10 to the 9th. And the Q that's making my electric field is this positive 0.45 millicoulomb charge. And so that ends up being 4.5 times 10 to the minus 4th coulombs. And I will give you a little trick there. I know that for me, we all have these little things that sometimes just kind of mess us up for some reason. And so if this is a decimal and I got to put it in proper scientific notation and I have to move it so many decimal places to the right, sometimes when I try to do it in my head, I goof it up. So I just want to tell you this little trick that you can actually type in. You know that a millicoulomb is 10 to the minus 3 coulombs. So you can actually type into your calculator 0.45 times 10 to the minus 3, and your calculator goes, that crazy student didn't quite get that right. Here, let me fix that. And so even if you don't type it in correct scientific notation, your calculator will automatically fix it for you. So even if you can't do that in your head, it's okay. Type it in as 0.45 times 10 to the minus 3. Your calculator will know what that means, and it will put it in proper scientific notation for you. Okay, so there's the Q, and the initial R was 0.33 meters. And then when I crunch all those numbers, I end up with 1.2 times 10 to the 7th volts. Now, I can't calculate the electric potential down here because I don't know what that distance is. That's where I got stuck. That's what I'm trying to find, is that piece right there. But I know delta V and I know V sub I, so I can calculate what the potential would be at that location, because delta V is V sub F minus V sub I. I know that delta V is negative 1.7 times 10 to the 6th volts, because that's what I calculated up here. And then I'm going to have V sub F minus V sub I, which is 1.2 times 10 to the 7th volts. Okay, so if I add that number to both sides, I come up with a V sub F of 1.0 times 10 to the 7th volts. Okay, now that I know that electric potential, again, that's capital V, not a little one. Now that I know that electric potential, now I can use the formula for electric potential and find out what that R is. So I'm going to use V sub F equals KQ over R. The V sub F is 1.0 times 10 to the 7th volts. K, 9.0 times 10 to the 9th, Newton meters squared over Coulomb squared. The capital Q is the fixed charge, so that's the 0.45. So that's the 4.5 times 10 to the minus 4th that I used before. And all that goes over R, because that's the one thing I didn't know. So when you multiply both sides by R, divide both sides by this 1.0 times 10 to the 7th volts, you end up with R equals 0.41 meters. Now, what is that number? That number is the distance from here all the way out to out here. So that's 0.41 meters. The question says, how far away will the particle travel before being pulled back? So I wanted to know this distance right here, so I just have to subtract these two now. 0.41 minus 0.33 is going to give me 0.08 meters or 8 centimeters. that it's actually going to be pulled, or it's going to travel before it starts being pulled back. So I know that in this chapter he does not really draw any diagrams at all. I find it very helpful to draw these diagrams, especially when you're trying to analyze which way are these going, and especially in something like this, because if you don't draw this, it may escape your notice that the final distance you find isn't actually the final distance that you're being asked for. So draw a diagram on all of these problems and make sure that you truly understand the physics of what's going on.